this video, we're going to look at the wave-particle duality of light. Electromagnetic radiation has been shown to have properties of both waves and particles, and this is called the wave-particle duality. The double-slit experiment showed that electromagnetic radiation clearly behaved as waves. The photoelectric effect showed that electromagnetic radiation behaved not as waves, but under certain circumstances, it behaved as tiny little particles of energy. So let's take a look at the photoelectric effect in more detail. First of all, this effect was first discovered by Heinrich Hertz in 1887, and then it was explained by Albert Einstein in 1909. And Albert Einstein won the Nobel Prize for explaining the photoelectric effect. So Hertz basically showed that shining a light on a metal caused electrons to be ejected. And whether electrons were ejected or not depended on the frequency of the light and not the amplitude of the light. Of course, if light is a wave, increasing the amplitude of that wave should increase the energy. So let's take a look at the photoelectric effect in a little more detail. Let's say we have our metal foil, and let's say we irradiate it or shine a blue light, which you can see represented here. Let's shine a blue light on that metal. When we shine the blue light on the metal, electrons are ejected. You can see the little electron being ejected here. So when we shine the blue light on our foil, we get the ejection of some electrons. What if we tried a violet light instead of blue light? Let's shine a violet light. Remember that a violet light has a greater frequency and shorter wavelength than blue light. So here is our violet light all the way at the end of the visible spectrum. Here's the blue light, and red light, we'll take a look at red light in a minute, is way down here. So violet light has a higher frequency than our blue light, and red light has a lower frequency. So here's our same metal, and here is our violet light. We're going to shine that on there. When we shine the violet light, we still get the same number of electrons being ejected. There is one difference though. The electrons that are ejected have a greater velocity. So the violet light ejects the same number of electrons as the blue light, but they have a greater velocity. Now, what if we tried a red light? We shine the red light onto our foil. Remember, the red light has a lower frequency than the blue light and the violet light. So let's shine the red light on there. When we shine the red light on the foil, no electrons are ejected. So if we decrease the frequency of our light below the blue light, we get no ejection of electrons. So the blue light had a greater frequency, shorter wavelength than the red light. It was able to eject the electrons, as was the violet light, but the red light could not. So how could we get the red light to be able to eject some electrons? Well, according to wave theory, if we increase the intensity or the brightness of the red light, we should be able to get some electrons being ejected, because the brightness or intensity of a light wave can be increased by increasing the wave's amplitude. Increasing the amplitude of a wave increases the wave's energy. So traditionally, if you increase the amplitude of a wave, you give that wave more energy. You can see over here we have a low energy wave and a high energy wave with a higher amplitude. And think about ocean waves. If you're standing in the water and you get hit by an ocean wave that's about 1 foot high, it may knock you back a little bit. If you get hit by an ocean wave that's 20 foot high, it's going to knock you way back, because that 20-foot high wave has a greater amplitude and therefore more energy. So according to classical wave mechanics or wave physics, waves with more amplitude, a greater amplitude, have more energy. And so by increasing the amplitude of our red light, or the intensity of it, we should be able to hit the foil with more energy and eject some electrons. So here you can see we're increasing the amplitude of our red light. And when we hit the foil, still no electrons are ejected. Well, that didn't work. So maybe we still need to increase the amplitude even more. So we can continue to increase the amplitude of our red light as high as we'd like, but we never get any electrons ejected. Well, that's not what we'd expect, though. If light behaved as waves, we should be able to get some electrons ejected by increasing the amplitude. But what if we increase the amplitude of the blue light? Okay, here you can see we're increasing the amplitude of the blue light. When we do that, we get more electrons ejected. So blue light at a higher amplitude ejects more electrons, but that didn't work for the red light. We can increase the amplitude of the blue light even more, and we continue to get more and more electrons ejected. So thinking of light as waves cannot explain what we would see. It would be expected, according to classical wave physics, that if you increase the intensity of a wave, you increase its energy. And by increasing the energy of that red light, by increasing its amplitude, we should get electrons ejected. So greater amplitude equals greater intensity. According to wave theory, though, as we mentioned, that doesn't work. So to sum up the conclusions of the photoelectric effect, or the results, there's a certain threshold frequency that must be reached before electrons are ejected. And that we saw that with the blue light. The blue light met that threshold frequency, and the violet light was above the threshold frequency, so we were able to get electrons ejected there. Decreasing the frequency below this threshold, no matter how much you increase the intensity of the light, you cannot get electrons to be ejected. If you increase the frequency above the threshold, the same number of electrons are ejected, but as the frequency becomes greater and greater, the electrons that are ejected are ejected with greater velocity. Okay? A second summary of our results: a threshold frequency must be reached before electrons are ejected. If you are below this threshold frequency, increasing the intensity of the light does not result in the ejection of electrons, and this is what is expected if indeed light behaves as waves. Above that threshold frequency, the intensity of light gives you more electrons being ejected. So how can you explain this if using the assumption that light is waves fails to explain this? Well, Einstein theorized that electromagnetic waves could be thought of as a stream of tiny particles called photons. The energy of the photon depends on the frequency of that photon. So by increasing the frequency of the light, the photon had more energy and it was able to eject that electron. So light, therefore, not only behaves as waves, but can also be thought of as small particles. So think about it: if you threw a ping pong ball at a glass window, you could throw as many ping pong balls as you want at that window, but the ping pong ball, no matter how hard you throw it, the ping pong ball doesn't have enough energy to break through that glass window. If you threw a baseball, that baseball would have enough energy to break through. So the particles in light would be analogous to the ping pong ball, which would be below the threshold energy, or the baseball, which would be above the threshold energy. So Einstein hypothesized that the electromagnetic energy occurs in discrete bundles or quantum, which he, of course, called the photon. So energy is quantized. The energy of a photon, as we said, is related to the frequency of that photon times a constant, h, which is Planck's constant. So the energy of a photon of light is equal to Planck's constant times the frequency. Remember that the frequency of light is also equal to the speed of light divided by its wavelength. So we could rewrite this formula as energy is equal to Planck's constant times the speed of light divided by the wavelength of the light. So each metal has a minimum energy needed to eject an electron. This is known as the work function. So for an electron to be emitted or ejected, the photon must have an energy, which we can write as Planck's constant times its frequency. The energy of the photon must be greater than the work function. The excess energy is the kinetic energy of the electron emitted. So we could write Einstein's photoelectric equation as follows. The energy of the photon, h times the frequency, is equal to the kinetic energy of the electron emitted times the work function. And you could think of the work function as the binding energy of the electron, or the energy required to remove the electron. So the kinetic energy, we could rearrange this equation. The kinetic energy of the ejected electron is equal to the energy of the photon minus the binding energy of that electron. Binding energy of that electron. So the binding energy of electron differs with the different metals. Here's a representative sample of some metals and their binding energy. So it's not a constant value. For example, platinum, the electrons are bound much more tightly than those in sodium. Sodium more readily gives up an electron. These are measured in electron volts, which is a unit of energy. It's just a little simpler to write than a joule for these very small values. So just a couple more things about the photon. The photon is considered the smallest quantity of energy or electromagnetic radiation. Much as the atom is the smallest unit of an element, the photon is the smallest unit of energy. A photon may be pictured as perhaps a small bundle of energy or quantum traveling through space at the speed of light. Sometimes it's called a wave packet. And the properties of photons have a frequency, a wavelength, a velocity, which is the speed of light in a vacuum, and an amplitude. Although they are particles, photons do not have mass or an identifiable form. So photons are massless particles. The intensity of the electromagnetic radiation, if we think of it as in terms of photons, the intensity of the electromagnetic radiation is equal to the photons per second, which is proportional to the amplitude. So if we think of light as a wave, its intensity is related to its amplitude. If we think of electromagnetic radiation as photons, the intensity is equal to the photons per second. So light can be thought of as having properties of both waves and as particles. And the reason we study this in chemistry is because this wave-particle duality not only applies to energy, but it also applies to electrons, as we'll see later. So these are very important things to have a good understanding of. Let's take a look at a problem. What is the energy of a photon with a frequency of 6.788 times 10 to the 5th seconds to the minus 1? Pause the video and give this problem a try. So we know that the energy of a photon is equal to Planck's constant times the frequency of that photon. So we could solve for the energy by multiplying Planck's constant times the frequency, and we get 4.498 times 10 to the minus 28 joules. Our units of seconds will cancel, And we have, of course, 1, 2, 3, 4 significant figures. So remember your sig figs and your units. So be sure you understand the concept of the wave-particle duality, the photoelectric effect, and the double slit experiment. Be sure you can solve some problems related to those topics.